Hello everyone, and welcome to this video titled Defining the Derivative. In this video, I'm going to be taking you through a preview of a Knewton Alta assignment that is titled Defining the Derivative. So please understand that this is a preview version of the assignment. So the questions that I'll be working on in this video may not be exactly the same questions you'll be seeing when you work on it on your own, but the objectives are all the same. The way I'm doing things, shouldn't change all that much to the way you're doing them when you work on it on your own. So hopefully this helps. Okay, so here we are at Knewton Alta. So again, you'll see the title of the section, the assignment for this particular course I am in. This defining the derivative assignment is for section 3.1. For right-hand corner, you should be seeing a mastery bar that tells you how far along you've gotten in the assignment. Next to that, an activity log, where you can see all the objectives in the assignment. So it looks like there are 6 objectives in this assignment, broken up into 3 sections. There's tangent lines, the derivative of a function at a point, and velocities and rates of change. And the way I have the settings, you can actually go and change what section you're in by clicking on Start on different sections. So right now I'm in the tangent lines section. So it'll throw questions at me from just these 3 objectives here and move me to a different section later, unless I want to change, but I will not be doing that. All right, then you have your current objective, which again, you can switch to a different section if you wish, if your instructor has those settings on. And then a question related to that objective beneath it. And then at the bottom of every question, you should see a feedback button. So if you notice there are any typographical errors, any mistakes in the question or the answer explanations, you can send feedback directly to Knewton support, and hopefully they're going to get back to you soon and help you fix whatever problem you have. I hope it's obvious that the instructor cheat button will not be there for you as a student. It's for instructors only to fill in answers for demonstration purposes. I will not be using this in this video. And then you will have, as a student, the More Instruction button. So if you're working on a question and you are at a particular objective and you forget the material or you'd like to brush up, click on More Instruction, Open Instruction, and some reading will come up or videos to watch or both on that particular objective, and hopefully that'll help you, get through the assignment. All right, so this first objective I'm given is find the slope of a tangent line using the second limit definition. Right, so if you look at the objectives, there's a first limit definition, second limit definition. Both of these are the same thing, just in a different look, different disguise. So I'll go over both definitions here with you right now. So again, the slope of a tangent line, this is also referred to as the derivative of a function at a particular point. So yeah, so first topic here, slope of tangent line. So suppose we are given a function y equals, f of x. Draw a little sketch here of I'll draw a nice continuous function. All right, something without a bunch of breaks or gaps or jumps in my picture here. It doesn't have to be, but so here's say x equals a, and I plug it into f here and that point. So here's the output, f of a. All right, so here's the point, a comma, f of a on the graph of some function. All right, so I'll draw a function that's, continuous here that actually goes through it smoothly. Right, like something like that, that way and that way, whatever, right? You can draw some function that passes through this point. So here's y equals, some function of x. So what we're asked to find is the slope of the line tangent to the curve at this point. So your tangent line would be this line here. It's the line that points in the direction the curve is moving in at that moment. So that would look like this, something like this. So here is this is the tangent line at x equals a here, right? Again, it points in the direction that the curve is going in at that moment. So what we're going to be asked to find then is the slope of the tangent line. We're looking at the problem. They're denoting this at the moment, they're denoting this as m sub, tan for tangent. Remember, m typically represents slope of a line, right? Y equals mx plus b. But then you have this subscript of tan to let you know they're talking about the tangent line. All right. So the big issue is, right, the big problem is I can't find the slope of a line when I only know the coordinates of one point, right? The only point on this line that I would know is this point a, f of a on my curve. So we use slopes of what are called secant lines, right? These will be lines that'll cut through 2 points on the curve. And then have the slopes of, and we'll see what happens to the slopes of those secant lines as they get closer and closer to the tangent line. So how do we do that? All right. So again, there are two definitions. They go over here, two different ways to think about this, but they really boil down to the same thing. So the first one is, okay, I pick any value that's not a. Right, so I'll put it over here. Here's some other x value. I'll just call it x for right now. That's not a, right? Because if you chose a again, you wouldn't get another point. So I'm looking to pick a value of x that's not a. And if I were to plug this in, right, that gives me this point here. So this point has an x value of, x and a y value of, f of x, right? The output when you plug x in. So here's the point x comma f of x. And I will draw another line through this point and the point that we want, the slope of the tangent line at. So look, here's now 2 points, you can dictate a line. Here's a line through those 2 points. And this would be called a secant line, and it looks like the color I chose is too close to the color of the original curve, so I'm going to do that again with the green here. Let's through the point x f of x and our initial point a f of a, right? So this would be cutting through multiple points, cutting through the curve, right? This does not point in the direction the curve is going in at any given moment. it just points me from one point to another on the curve, right? It's through 2 points, secant line. Now the slope of this secant line that I just drew, again, it's going to be denoted M sub SEC, secant. It's just rise over run. Remember how, hopefully you remember from algebra how to calculate the slope of a line. So it's change in y over change in x. Right, so I've got these 2 points on it, a f of a, x f of x. So I'll do this point minus that point. I'll do the y coordinate of this point, f of x, minus the y coordinate of this point, f of a. And there's, the rise, the change in the y coordinates, divided by, and then the run. And I do the change in the x coordinates, in the same order, x, so x minus a. And you could do the other order, f of a minus f of x, but then you have to divide by a minus x if you do the other order. So same thing. Now, hopefully you can see, this is not a great, I picked it over here, this other point. This secant line should be an approximation, should be close to the tangent line. And, or, most functions, if I were to have x, this x value I chose, that's not a, pick x to be closer and closer to a. So say it were here, then I'd have this point, and then this would be my secant line. So here's another secant. And you see how that line I just drew would be closer to being the tangent line. Or if, now if I'm really close to A, if this were my x value, I'd be at this point on the curve, and then this would be my secant line. And you can see that, the secant there, very close to being the tangent. So what we're doing is we're having this x value that's not A get closer and closer to A, and then the slope of the secant line should be getting closer and closer to the slope of the tangent line. So we'll say the slope of the tangent line is the limit as x approaches A of the slope of these secant lines. So this is the first definition. So the slope of the tangent line, at x equals A is the limit as x approaches A. I could have done this on the right side as well, from either side, of the slopes of these secant lines, which again I wrote up here. So we have the limit as x approaches A of, and then the change in the y coordinates, the value of f at x minus the value of f at A divided by the change in the x, right? X minus A, rise over run. Okay, so this is one definition, and I believe this is the first definition that they talk about when they differentiate between first and second definitions. So yeah, this is one definition of the slope of a tangent line, a derivative. We'll get to the word derivative later. The other definition, which is the one that's being asked for here. Now you can use either one. Right? I'll show you. You can use either one. So the other definition, which is equivalent to the first one, so I'll draw a very similar picture, almost exactly the same picture as I drew on the previous page. So again, we have a XY plane here. Here's x equals A, and I plug it into my function. Again, I'll get some point with an output of, f of A. So here's the point, a comma, f of a, ordered pair. And again, I'm going to draw some nice curve going through here, some function, and maybe doing this like I had earlier, right? Something like that. Here's y equals, some function of x. All right. And we want, the slope of this tangent line, right? So at this point where x is a, here's the line that's, pointing in the direction, just glancing off the curve, right? Points in the direction that the curve is going in at that moment. So there's the tangent line I want to find the slope of. So again, I only know one point on it, so I go somewhere else. This time I'll go over here. It doesn't matter, left side of A, right side of A. I go to some other value, but instead of calling it, X, like on the previous page, we're going to say that, we move left or right by some horizontal change. So they're going to represent this horizontal change by the letter H, where, H is not 0, right? Because if H were 0, the horizontal change were 0, I'd be at A again and not get a second point and not be able to form some secant line. So A, and then I add this horizontal change to it. So the other value on the x-axis that's not A is represented by A plus H. And then this gets plugged in. This A plus H value takes me to another point on the curve. So here's the point, with input A plus H, and then output, f of A plus H. There's a output f of A plus H, y coordinate f of A plus H. And then here's this, secant line. I draw a line from this A plus H, f at A plus H point through the A f of A point, and we get, a secant line. And you see how, it's close. It's not exactly the same as the tangent line, but it should be, if you're close enough to A, the secant line, should be close to the tangent line. Right, so their slopes should be approximately equal. So once again, if I want this secant line to be better and better approximating the tangent line, I need to move this other point that was off of A toward A. Well, to do that, to have this value get close to A, I need H to get closer and closer to 0, right? The smaller this H is, the closer A plus H will be to A. So again, so here's the other definition, the second, definition they're talking about. The slope of my tangent line will be the limit as this, horizontal change, this H value goes to 0 of the slope of these secant lines. But here, so we got the limit as H approaches 0. But here, the secant line goes through this A plus H, f of A plus H point, and A f of A point. So the rise here, right, when I'm taking the slope of the secant line, take the change in the y coordinates, and I'll do this one minus this one. You have f, the value of f at that A plus H input minus the value of f at A, and that would be the rise, the change in y. And then the change in x would be A plus H minus A, or just this H, right? That's the horizontal change. That's what this H is representing. So down here is just simply the letter H representing the change in x, the horizontal change. So this is actually the same. It'll give you the same result as the first definition. Right? And again, I will show you. It's just another way to look at it. All right, so we have two limit definitions of this slope of a tangent line. So I'm going to show you how, I'm not going to do it for every question, but you'll see in this first one how it doesn't matter which one you use, which definition, you'll get the same result. So look, now we're asked to find the slope of the line tangent to the graph of f of x equals 3x plus 6 at x equals -1. Now, this function we are given is already a line, right? This is mx plus b, this is y equals 3x plus 6. So no matter where I'm at, the tangent line will just be this line, right? You're going in the direction that the line is going in. And the slope of this line is 3. So what we'll end up seeing is that the slope of any tangent line, so even the tangent line at x equals -1, will be 3 as well. And I'll draw a little picture of that. So we're given here, the function f of x equals, 3x plus 6, which is pretty easy to graph. It's just going to be a line with a slope of 3 and a y-intercept at 6, right? So here's, say here's 0, 6. And, we're concerned with x equals -1, right? We're asked to find, the slope of the tangent line at x equals -1. So I'll plug in -1. This would be -3 plus 6, you get +3. Okay, so here's the point in question. This is the one that we care about, -1, 3. And it's, again, it's a line, straight line graph. Here's the graph of f. And so yeah, so remember what I was saying earlier, you take this point here, this line that we just drew, that is the tangent line, right? Tangent line goes through our point and goes in the direction that the curve is going in. So this is also the tangent line at any point, really. Right? This is a really simple thing when your graph is a line already. So slope is 3. This is going to be 3. Now let's use the definitions to show that, right? So that first definition was I take a value called x that's not -1, right? And if I were to plug it in, there'd be this other point with input x and then output 3x plus 6, right? The output would be f of x. And then the slope, and my secant line, again, is the line, right? The slope of the secant line is, 3x plus 6. All right, that's the value of f at any x minus, and then the value of f at -1, the other y coordinate is, 3. And then this gets divided by, the change in x minus -1. And then we're going to see what happens as x approaches -1. All right, so using that first definition, right, the slope of the tangent line at this point, -1, 3, be the limit as this value of x approaches -1 of, and then our expression here, which of course will simplify in a second, 3x plus 6 minus 3 divided by, and then x minus -1, right, is x plus 1. Okay, and we're evaluating this limit. So now if you go back to, there was a previous video on the limit laws, and in that you saw, the indeterminate form 0 divided by 0. You'll notice that when you're calculating, when you're trying to find these limits to give you the slope of a tangent line, if you leave things as is, change in y over change in x like this, and you just plug the value in, right? You assume, hey, I can just use the limit laws and do a direct substitution here. If I were to do it as is, right, you'd end up with the numerator being 0. All right, this would be 3 minus 3, and the denominator would be 0 as well, -1 plus 1. So remember that's indeterminate. I'm just going to write IND. Nonsense, right? It doesn't tell you anything. So then we got to simplify the expression into some equivalent expression where I can apply the limit laws and just do a simple direct substitution. So we have the limit as x approaches -1 of, and then 3x plus 6 minus 3, that would just be 3x plus 3 divided by x plus 1. And the 3x plus 3 can factor, right? This is the limit as x approaches -1. 3x plus 3 has a common factor of 3, right? So that's 3 times the quantity x plus 1. And then you see in the denominator, there's only the factor of x plus 1. I'll put parentheses around it. It's the only factor. And since x is not -1, right, we're approaching -1. These are both the same non-zero number, so they'll divide to be 1. And I'm left with the limit of a constant, right? We have the limit as x approaches -1 of just, the number 3. So the slope of any secant line would be 3, right? Because again, any secant line, you take any 2 points on this and draw the secant line, it's the line again, which has a slope of 3. And remember the limit of a constant is that constant, right? No matter what x is, this 3 will stay 3. So here we go. There's our, slope of this tangent line I drew. Right? Which again is, so that's a shortcut for you. If your function is linear, like this one was, the derivative, the slope of any tangent line will just be the slope of that line. Right, so 3. Let's keep that in mind for maybe future problems. Now the other definition, okay, so that was the first definition. I'll show you, right? The other one, I said or, right? You don't have to do both. I'm just going to do both for this first one. And here was the point we care about. And then the tangent line, is the line, goes in the direction that the curve is going in. So yeah, the other way to do this was, so here is -1. I go to -1 plus h, right? Add some horizontal change. So here's this other point, with -1 plus h as the input. And then, 3 times -1 plus h plus 6 as the output, right? So again, just plugging in -1 plus h for x into my rule for the function. So this other definition was, the slope of the tangent line, and I'm going to have this, -1 plus h get closer to -1. And to do that, I need h to approach 0. So it's the limit as h approaches 0 of, and then the value of the function at -1 plus h, right? So 3, and put in parentheses, 3 times -1 plus h plus 6, right? This is the value of the function at -1 plus h, then minus the value of the function at -1. So again, this point and this point, which is 3. So that's all in the numerator there, and then divided by, -1 plus h minus -1, or just h, right? Again, just h, just the horizontal change in the denominator. So again, if you left it this way and just plugged in 0 for h, you'd end up with 0 divided by 0, right? This will be happening whenever you set up these limit definitions of the slope of a tangent line. So I got to manipulate this expression. Now, if I were to, I'm going to kind of skip ahead here. This is a little algebra. But if I were to distribute this 3, you'd have -3 plus 3h plus 6. So this all told here would be negative, is again, it'd be 3h plus 3. It'd be 3h plus 3. Right, you'd have negative 3, then plus the 6 would be positive 3, and then, plus 3h. So 3h plus 3 for this expression, defined at negative 1 plus h. And then 3h plus 3 minus 3 would just be 3h, right? So the numerator of this turns into just, 3h, and then divided by h. And you can see the h's canceling, right? Again, h is not 0. It's approaching 0. So these h and h are both the same non-zero number, so they'll divide to be 1. And now I have, once again, the limit of a constant. Right, the limit as h approaches 0 of just 3. And, that would just be 3 again, right? No matter what h is, 3 is 3. So you see, either way I do it, I end up with the same slope of 3. So back here I'm entering, slope of tangent line is 3 at x equals negative 1. And again, because it's a line, this was a linear function, it didn't matter what x value they gave me. It's, the slope of the tangent line is the slope of the line. Right? The tangent line would be that line all the time. Submit. And then when you get something correct, some green banner will show up telling you, good job or whatever. Give you some encouraging words. If you got it wrong, a red banner will show up, with still some encouraging words like, not quite, try again, you can do it, or something like that. And then below, you always have, whether you get it right or wrong, an answer explanation. So you see the second definition was that one I mentioned, right, for the slope of a tangent line. I would suggest reading through these answer explanations, whether you get something right or wrong. Definitely if you get it wrong, right, try to read through them, figure out why it was wrong, where you went wrong, and hopefully you can learn from your mistakes for future questions. And if it was correct, even if you were right, look through these, just glance through them, because maybe you did it in some really roundabout, tedious, long way, and they're doing it in a way that you like better. That's more efficient, and you might want to try it when you see another question like that. And again, they draw a picture kind of like I had. I mean, they did it in Desmos, it looks like. All right, so continuing on, so see they slip. So they switch to, and I'll use the definitions they're asking for. Again, it doesn't matter which. So this one's find the slope of a tangent line using the first limit definition. So notice here, this function, this is not a line, right? This is a quadratic function. The graph would be a parabola, opening down. So you can't tell immediately what the slope of some tangent line is here, right? This is not a straight line curve. So it really does matter now where we're at. So this is at x equals negative 1. And I'll try to draw a sketch of this as well. All right, so my function and this quadratic function, negative 2 times x squared minus 4x minus 2. I'll show you the graph of this. Just remember that the axis of symmetry would be, the opposite of b over 2a, right? So positive 4 over negative 4. So at negative 1. And then if you plug, the value, this is actually the value we care about, right? The value of f at negative 1 would be, negative 2 plus 4, which is positive 2, and then minus 2 is 0. Okay, so here is the vertex, all right, negative 1, 0. And then that, remember, would be the highest point of this. This would be a parabola opening down. You would have a y-intercept at 0, negative 2, and it's this parabola opening down. And I can go to Desmos and show you a better picture, but yeah. But this -1, that's what we're asked to find, right? We're asked to find the slope of the tangent line to this curve at x equals -1. So look, this one here, if I draw the tangent line, again, the direction the curve is at the top of a hill or the bottom of a dip. Okay, so like this or like this. If you're at the top of that hill or the bottom of that dip, your tangent line will be horizontal, right? So that actually happens here. So horizontal tangents at these tops of hills and bottoms of dips. These gotta be curvy though, bumpy. Curvy hills and curvy dips, not pointy. So you got horizontal tangent lines at these kinds of points. So at this point here, the tangent line would just be the x-axis. All right, so here's the tangent, and I can actually, if I know what the picture looks like, you know, like in the last example with the straight line graph, if I know that this point is at the top of some curvy hill like this, or the bottom of some curvy valley, I know the tangent line's got to be, horizontal. And remember, horizontal lines have a slope of 0. All right, so eventually I'll still go through the problem, right? But the slope of the tangent line here is 0. Now, of course, if you were somewhere else, if I was at this point or this point, right, over here, tangent lines would have a positive slope. Over here, tangent lines would have a negative slope. Okay, so it's not always 0. Right, but at this particular point at the top of the hill there, I know it's going to be 0. Now let's go through the definition though. All right, so remember that this is the one where they're asking me to use the first limit definition. So that's where I go to some value called, I'm going to call it x, that's not -1. Plug it in, say I'm over here. Again, it could be on the right side or the left side. So here's x, input x, output f of x. I'm not going to write all that, but this is my output, this -2x squared minus 4x minus 2. And then here would be my secant line through this point xf of x, and then through the point, -1, 0. This would be, my secant line, and then we take the slope of the secant line and then have x approach -1 to get closer and closer, to this slope of a tangent line that they want. So using that first definition, right, the slope of the tangent line that I'm looking for at x equals -1 will be the limit as this x value approaches -1 of, and then the slopes of my secant lines. So again, it's the value of f at x. So that's this, -2x squared minus 4x minus 2, then minus, the other y coordinate, the value of f at -1. So minus 0. And then all this, divided by the change in x, which would be x minus -1. So like the earlier example, when you set these up initially, they're going to be in that 0 divided by 0 form, right? If you were to plug in -1, numerator be approaching 0, the denominator be also approaching 0. So I got to manipulate this, right? So this is the limit as x approaches -1 of, now the numerator, minus 0 doesn't do anything. So that's -2x squared minus 4x minus 2. I'm going to start factoring this. This is -2 times, x squared plus 2x plus 1 divided by, and then just down here is, the only factor in the denominator would be x plus 1, right? X minus -1. And x squared plus 2x plus 1 is x plus 1 times x plus 1, right? X plus 1 squared. So the limit as x approaches -1 of, -2 times x plus 1 squared divided by x plus 1. And since x is not -1, one of these x plus 1s and this x plus 1 would be the same non-zero number, so those divided to be 1. So this will cancel just one of these, though, so that becomes just x plus 1, to the first power. And now I have an expression where I can just kind of use the limit laws and make a direct substitution here. This would be the limit as x approaches -1 of -2 times x plus 1, which would be -2 times 0, which is 0. So like I said earlier, right, you could have probably just said that if you knew, from the graph that you were at the top of a curvy hill or the bottom of a curvy valley, right? The tangent lines in those places are horizontal and would therefore have a slope of 0. So this has a slope of 0, this tangent line. So that's what I'm putting in here. Slope of the tangent at x equals -1 for this particular function is 0. Again, they go through all the stuff I just went through. And show you the picture, right? Here's the curve. You're at the top, the point we're looking at is at the top of this curvy hill. Tangent lines at those places are horizontal, right? If you were standing there and looked in one direction or the other, you'd be looking horizontally. You'd be looking straight out. Yeah. All right. All right. So still using that same, first limit definition. All right. So I'm gonna still draw some graphs. All right. Some of these, if the curves are easy to draw, I will draw them. Otherwise, I'll go to Desmos or something. And hopefully with enough practice, you can get through these without looking at a drawing. So once again, we're finding the slope of this tangent line to the graph of this square root function at x equals 5. So again, not a straight line, right? If it were a straight line, I would just say, hey, the slope of the tangent line is just the slope of the line. But this is not a straight line graph, so the slope of the tangent line does change when you go to different points. All right, so here we're given different marker here, sorry. So we're given f of x equals, the square root of x minus 1, but you should know what that looks like based on previous algebra or pre-calculus experience. So this would have the point, 1, 0, and you could only plug in values greater than 1, right? So that, because it's an even root and only has real number outputs when the expression inside is non-negative. So it looks something like this, like the top half of some parabola opening to the right. So there's the graph of f. And we're concerned with, this. We want to find the slope of the line tangent to this curve at x equals 5. So if I went to 5 here, let's say 5 is over here, plug it in, you get an output of 2. Okay, so f of 5 is, that'd be the square root of 4, right? So positive 2. So I got the 0.52. And if you were standing there and looking straight out, you'd be looking in this direction, right? Here's the direction the curve is going in. Here's my tangent line. So that's, hopefully it's obvious that that is not horizontal like the last example. So this is not going to have a slope of 0. In fact, it looks like it has a positive slope, right? It's rising as I go to the right. So hopefully when I'm done, I end up with a positive number for this, slope of the tangent line. And of course, if it were falling as I go to the right, I'd hope for a negative number, right? Negative slope. So remember that this is in that first definition objective. All right, so remember that goes is I go to some other value called x in the domain that's not 5. I plug it in. There's x comma, f of x, which is the square root of x minus 1. And then here's the secant line going through these 2 points, this point and the point in question, right? Secant, no, it's not a great drawing, but the secant should be close to the tangent, right? They're not exactly the same. And then we'll find the slope of the secant line and see what happens as x, approaches 5. Right, so the slope of the tangent line in question is going to be the limit as x approaches 5 of, and then again the change in output. So f of x is the square root of x minus 1 minus the y coordinate at 5, 2 here. F of 5 is 2. So change in the y coordinates between these 2 points divided by x minus 5, right? The change in the x coordinates. So once again, if you left it this way and just plugged 5 in, it would be in the 0 divided by 0 scenario. So we got to manipulate this somehow. And if you recall from the limit law video earlier, with these square roots involved, never a bad idea to multiply the numerator and denominator by the conjugate of this radical expression. So that would be the square root of x minus 1 plus 2, and a minus b, a plus b conjugates. And do the same to the denominator, right? The square root of x minus 1, then plus 2. And remember, when you multiply conjugates, you get a difference of squares. So this is the limit as x approaches 5 of, and then in the numerator, I'd have, the square root of x minus 1 squared, which is just, x minus 1, then minus 2 squared, so minus 4. And then denominator, I've got this, factor of x minus 5 still, multiplied by that conjugate, right? This square root of x minus 1 plus 2. Now look, I'm not going to save a step here. This numerator, x minus 1 minus 4, that is x minus 5 when you put them together. And since x is not 5, these x minus 5s will be the same non-zero number, so they will divide to be 1. So don't forget, though, when an entire numerator or entire denominator cancels, there's still technically a 1 there. So we have the limit as x approaches 5 of 1 in the numerator divided by this, conjugate from earlier, the square root of x minus 1 plus 2. And now I have something where I can just do a direct substitution to evaluate the limit. So this would be 1 divided by, and then this is, when I plug 5 in, 5 minus 1 is 4, square root of 4 is 2, and then 2 plus 2 is 4, right? So the denominator is just 4. So there's the slope of this line. This tangent line to the curve at this moment has a slope of 1/4. So that's why I'm going to enter. So slope of tangent equals, 1/4. Guess you could also put 0.25 because, the decimal ends. And that would also be an exact value. Great. All the same stuff I did there. There's a picture of it, right? Nice better graph. The tangent line at this 0.52 with a slope of 1/4 going in the direction that the curve is going in at that moment. All right, so this one says, find the equation of a tangent line using a limit definition. So a limit definition, right? You can use either one. I'm going to kind of fly by this one, all right? Oh, no, I'm not. Uh, this is a little different, right? Find the equation of the tangent line, not just the slope, right? So not only do we need the slope, but also, what is the equation of that tangent line? Now this one will be simple though, because the function we're looking at is a line. This is in the mx plus b negative 2x plus 7 form, right? So I'm not going to go through the whole definition thing. I already told you, if you have a linear function, it doesn't matter where you are. The tangent line is that line. So you'll see, in fact, that this 7 minus 2x is the equation of the tangent line, y equals 7 minus 2x, but I'll draw it. All right, I'll draw it. Again, linear functions, finding these tangent lines should be quite simple. So again, here was the function we're given, right, y equals f of x equals 7 minus 2x. I'll draw a little picture. So this has a, y-intercept of 0, 7. So there's, 0, 7. And a slope of negative 2. So, if I went down 2 and then right 1, 1, 5, x equals 1, y equals 5 should also be on this. And here's your function. Right, there's the graph of f, right? This f 7 minus 2x. Straight line graph. Now they're particularly asking for at x equals 2. All right, so here's 2. Now when I plug 2 in, f of 2 is 7 minus 4, so 3. So this has, I'll make this bigger, right? This is the point we're concerned with, 2, 3. And like I said, hopefully you see that the tangent line is the line, right? If I draw the line going in the same direction as the curve, the tangent line is the line. So, so the slope of the tangent line is also negative 2, just like the slope of the line. The tangent line is the line. So I've got a slope, and then we've got a point, right? The point that we're concerned with, the point that we're at is the point 2, 3. So remember, when you have the slope of a line and a point on that line, you can write an equation for the line, right, for the tangent line, which should end up just being negative 2x plus 7, right? It's the same as the line that, that we were given, but I'll show you, right? So equation for the tangent line. Now, remember there were multiple forms of an equation of a line. One of them was point slope. I find this a very easy one to go into. So that's where you just write, the change in y. So y minus, the y coordinate of my point equals the slope, so negative 2, multiplied by the quantity, and then the change in x. So I did y first, then minus the y coordinate, so I got to do the same with the variable x minus the x coordinate of my point. And this is a perfectly valid equation for a line, this line here. But I think based on the look of it, right, see how they got y equals y by itself. So looks like they want it in, slope, slope intercept form. But that's easy to do once you have point slope. I would just take this here and solve for y. So distribute the negative 2, and then I would add 3 to both sides. Right? So if I do that, you get y equals, this is negative 2x, and then you'd have plus 4, and then plus 3, so plus 7. And I already told you, right? I'm not going to do all this in the future. if the function they give me is a line, right? So they gave me a line, that is the tangent line as well, right? No matter where you're at. So there we go. Y equals, negative 2x plus 7. I didn't use any definition of the derivative there, the slope of the tangent line, because again, I already mentioned when you have a line, the slope of the tangent line is the slope of that line, right? No matter where you're at. So simple enough. They go through the whole thing fine, but again, see that they don't even have a red line up here, right? There's a 0.23. The tangent line is the line. All right. All right, so here's one where, again, we're asked to find the equation of a tangent line using the limit definition. All right, so here's another one. Okay, this one. Okay, this is quadratic, not a line. So I do have to do a little work here. All right, the slope of the tangent line to some non-linear curve changes depending on where you're at. So I have some paper here. So the function we're given again is quadratic, some parabola shape. If you go to a graph, and I'll do a sketch of it again here. So here's the sketch of this. So quadratic, the vertex would be at, again, the opposite would be 4 divided by 2 times a would be negative 2. 4 divided by negative 2 is at negative 2. And if I were to plug negative 2 in, this would be, the opposite of 4, negative 4, and then plus 8 would be positive 4, plus 1 is 5. So the vertex is at the point, negative 2, 5, and lead coefficient's negative, so it'd be opening down, have an intercept of 0, 1. 0, 1 would be the y-intercept. And then using symmetry, and we're concerned with, we're trying to find the equation of the tangent line. At, x equals negative 4. Using symmetry, at x equals negative 4, it should also have an output of 1. I'll make this a bigger point. There's the point, negative 4, 1. And you can check that. So here's my point. The point that I'm at. F of negative 4, right, with the opposite of 16, negative 16. Plus 16 is 0, and then plus 1 is 1. Right? So we have a point. Again, negative 4, 1 on our curve. Right? So here's the curve, the rest of the curve. Right? The parabola would look something like this, opening down. Okay, so there's the graph of f. So what we want is the tangent line at this point, right? So again, points in the direction that the curve is more glancing off the curve. If you were standing there and looking straight out in the way the curve is going, you're going that way, right? So here's my tangent. Now, clearly this tangent has a positive slope, right? So I have a point on the curve, negative 4, 1. Now I want the slope. And this is where that, definition is going to come in. Now they're saying use, any definition. Right, it says, find the equation of the tangent line using a limit definition. So I personally like that first one. So I'm going to keep using that if they don't say otherwise, right? And again, you can use either one you want, whichever one you like better every time, and you should be fine. So again, what happens is I take a value called x that's not negative 4, plug it in, right? It gives me some other point on the curve. There's x comma f of x, right? So the y coordinate is this negative x squared minus 4x plus 1. Draw the secant line through those two. And, take the slope of the secant line and have x approach negative 4. So the slope is, m tan here. That's the limit as x approaches -4 of, and then the slope of our secant lines. So the y-coordinate at x is this. So we have this, negative x squared minus 4x plus 1. And then minus the y-coordinate at -4 was 1. And then all that divided by the change in x, so x minus -4. All right. So at the moment, right, this is one of those 0 divided by 0 limits. So I got to mess with it. So this is the limit as x approaches, -4 of. Now when I take this and subtract 1, then the 1's will go away. So this will be -x squared minus 4x. Those both have, the opposite of x as a common factor. So I'm going to pull that out. The opposite of x coming out. And if I remove the opposite of x from these two, the other factor will be x plus 4. And the denominator would also be x plus 4. And since it's the only factor down there, can't factor any further. I'm putting parentheses around it. And then, since x is not -4, these x plus 4s are the same non-zero number, so they'll divide to be 1. So I'm left with just the limit as x approaches -4 of -x. So that'll be the opposite of -4, so +4. So the slope is +4. So putting these two things together, I can write the equation of my tangent line, the equation of this tangent line I drew. So again, in point slope form, that would simply be, y minus, 1 equals the slope 4, and then times the quantity, x minus -4, which would be x plus 4. But they do have the y equals in the problem again. So I'm going to put this in points slope-intercept form. So I'm going to add 1 to both sides, distribute that 4, so I got y equals, 4 times x, so 4x. And then 4 times 4 is 16, plus 1 would be plus 17. And so here's the equation in slope-intercept form of this line that I have drawn here, tangent to the curve at the point that they wanted. So that's what I'm entering. So they already got the y equals. So I'm entering the 4x, plus 17. And again, they go through it here. There's the drawing, kind of again, similar to what I had earlier, definitely better than what I had earlier, where you can see the tangent line and all that. So we're back to that second definition with the h in it, right? Limit as h approaches 0 of the slopes of the secant lines. So same thing, but not the equation though, right? Now we're back to just being asked for the slope of the tangent line. So find the slope of the line tangent to the graph of this rational function, right? F of x equals 3 over x plus 1. Again, that's not a line, so it's not simple, right? Again, if it's a line, you should have no problem. That is the tangent line everywhere. I know I've been saying that a bunch. So anyway, this one, I gotta actually do some thinking. The tangent line will change depending on where I'm at. So we're gonna focus at being at, x equals -3. So here we are. And I'll draw a sketch. This is another one where, based on algebra and pre-calculus experience, this is a relatively basic rational function I should know the graph of. So I have f of x equals 3 over, x plus 1. Again, quick sketch here. Now this would have a vertical asymptote at -1. I'll do a little dotted line here. And also horizontal asymptote of 0, y equals 0, and you'd have 0, 3 on it, and part of the curve looking like this. So going through 0, 3, so approaching positive infinity from the right of -1, and it would approach negative infinity from the left of -1. Now, the value we're concerned with, right, they said find the slope of the tangent line at, x equals -3. So I'm going over here, right? Here's -3. Now, if x were -3, you know, here's f of -3 would be 3 divided by -2, so -3/2, -1.5. So the output -3/2. So that's this point here. I'll make it bigger. There's -3 comma -3/2. Right? And the graph is doing something like this, approaching the x-axis that way and approaching this, vertical asymptote going down forever there. So there's the graph of f, right? This branch and this branch. And what we want is this tangent line slope, right? This line here. It just glances off the curve at that point, points in the direction that the curve is going in at that moment. So this one looks like it has a negative slope based on my drawing, right? So when I end up with this, going through the definition, should end up with a negative number, hopefully. All right, so this second definition was I went to a different value called -3. Right, so we're focused on -3. I add, some h to it, -3 plus h, and that would take me to another point on the curve with input -3 plus h and output, f of -3 plus h. And then here's the secant line, right, going through those 2 points, right? There's my secant, and take the slope of the secant line and have h approach 0, right? Have h get closer and closer to 0. That way, -3 plus h will approach -3. So yeah, this other definition was, slope. So the slope of this tangent line will be the limit as h approaches 0 of the value of f at -3 plus h. So I replace x with -3 plus h. So that's 3 over, -3 plus h, then plus 1. And I don't need parentheses there. It's not being raised to powers or multiplied by anything. But if it were being raised to powers, if the x were being raised to powers or multiplied by something, then I would put parentheses around it. Then minus the value of f at -3, which was -3/2. Right, so that's the change in output divided by this h, right? And it'd be -3 plus h minus -3, right? The change in x, the horizontal change. That's what h represents. H for horizontal. All right, so again, as is, this is, one of them 0 divided by 0 limits, indeterminate forms, can't tell you what it is, so I got to manipulate the expression. Okay. So we have the limit as h approaches 0. Now this first expression here is, 3 divided by, this is really just h minus 2 down here, right? Positive h and then -3 plus 1. So I got the h minus 2, and that's the only factor down there. And then plus, right, minus negative, so plus 3/2. And again, all this divided by h. All right, so remember there was multiple ways you could simplify. This is one of those complex fractions. So one way would be to get the numerator together as a single fraction, right? Another way would be to take the entire numerator, right, everything above the main division, and the entire denominator, right, this h down here, and multiply by the least common denominator of all the denominators of fractions within the fraction. I know that's a lot of saying there. the LCD, the least common denominator, would just simply be 2 times h minus 2, right? And those are the only denominators I see. There's 2, h minus 2, and 1, right? This thing down here is technically h over 1. So I multiply by those, 2 and h minus 2h, not x, sorry, h minus 2. Same down here, 2 times h minus 2. Now up top, there are multiple terms. It's a sum, so I got to distribute this, right? Multiply each of those, and that should cancel away all these smaller denominators. So I'm left with the limit as h approaches 0. In this first fraction here, the h minus 2 would go away, so I'd have just 3 times 2, which would be 6, plus, then in this second fraction, the 2 would go away, so I'd have just 3 and the quantity h minus 2 left over in that one, divided by, and then down here, I have 2 times h, h times 2, 2 times h minus 2. Those are all the factors of that denominator now. Then simplifying the numerator here, this is 3h minus 6 plus 6. So that ends up being just 3h. So I got the limit as h approaches 0. Numerator now is just 3h. And the denominator is, 2h times h minus 2. And because h is not 0, these factors of h in the numerator and denominator can divide to be 1. And now I simply have 3 in the numerator and 2 times h minus 2 in the denominator. If I have h go to 0, that's 3 in the numerator, and then 2 times negative 2 in the denominator. So this is negative 3/4 over ln. Okay, so the slope of this line, which I said would be negative, right? We got a negative number, so great. The slope of this line tangent to the curve at this particular point where x equals negative 3, the slope of that tangent line is, negative 3/4. So that's what I'll enter, negative 3/4. Wonderful. And again, they probably have a nice picture down here. Look at this, right? So there's your point, negative 3, negative 1.5 for the y value. And this, tangent line at that point, tangent to the curve with a negative slope, right? A slope of negative 3/4. All right, so back to using the first limit definition. Okay, so this time, all right, I've done a bunch where I've already graphed. I'm just going to do it without graphing now. All right, hopefully after enough practice doing this enough, you'll be able to find these slopes of tangent lines, again also known as derivatives, without looking at a picture. Pictures are nice, they give you an idea, right? Like back, this picture from the last example, right? I could tell from the picture that I should get a negative number for my slope of the tangent, right? That's really all it's going to tell you. So I'm going to set this up, and write this out and do it, with just the definition and only the definition. Right? And they want that first definition here, right? So here's our function, right? F of x is another simple rational function. You got 2 in the numerator, x plus 1 in the denominator. And we want the slope of the tangent line at, x equals 2. All right, so because I'm not drawing a graph this time, I'll write out that definition, right? The slope of the tangent line at x equals 2 would be the limit as x approaches 2. Because again, we're going to be at 2, and then go to some other x value that's not 2, find the slope of the secant line, and then have x approach 2 to get the slope of the tangent line. So the rise, right, would be the value of f at that x minus the value of f at 2. That's the rise, the change in the y coordinates, and then divided by the change in the x coordinates, x minus 2. All right, so we got the limit as x approaches 2. Now, the value of f at x is this, 2 over x plus 1. Again, that's the only factor of that denominator. And then minus, now the value of f at 2 would be 2 over 3. Right? Replace x with 2, that'd be 2/3. And then divided by this x minus 2 down here. And again, that's the only factor down there. And you could write this as x minus 2 over 1 if you wished, but it's all right leaving it this way. So like the last problem with the rationals, and you set this limit up of the secant line slopes, you end up with the complex fraction. So I'm going to do the same thing as the last example, right? I'm going to multiply the entire thing up here, this down here, by the least common denominator of all the denominators I see, right? 3 and x plus 1 and 1. So that's just 3 times x plus 1. So times 3 times x plus 1. I'm going to do that to the top and the bottom. Now, once again, up top, I need to distribute because there's a difference, right? So I'm going to multiply both of these by this 3 times x plus 1. So we have the limit as x approaches 2. Now the first fraction here, the x plus 1s would go away, so I'd have 2 times 3 left. That would just be 6. Then minus, and then the second fraction multiplied by this, the 3's would cancel, and I'd be left with 2 in the quantity x plus 1. Right, so that's all in the numerator, and then the denominator has these factors. I'll put the 3 in front. 3 times x minus 2 times x plus 1. And nothing canceling down there. All right, then if I completely simplify the numerator, right, I'd have to distribute this negative 2. So that'd be negative 2x minus 2, but then, plus 6. Let's just go through it. It's 2 over x minus 2. So again, numerator, sorry, just double checking some stuff. All right, so we got, so again, this would be negative 2x, and then minus 2, plus 6, plus 4, and that can factor a little further as well. I'm going to leave the denominator factored. So this up here, I'm just going to do this here. Negative 2x plus 4, I can factor out negative 2. And if I do that, you'd have x minus 2 as the other factor, and then I can see the x minus 2 going away. All right, those are divided to be 1. So the numerator is now just negative 2, and the denominator has this 3 times x plus 1. And if x approaches 2, then the numerator is negative 2, and the denominator would be 3 times, 2 plus 1, 3 times 3. So negative 2/9 is the slope of the tangent line that they are asking for. That's all we're asked for, right? Just the slope of the tangent line, that limit using the first definition there, negative 2/9. And they do have the drawing, right? Here it is. So again, the point 2/3, right, would be on the graph. And you can see the tangent line to that blue curve, right, with a negative slope. And we said it was, negative 2/9. All right, so I'm going to not even write anything for this one. I've been telling you a bunch. This is a linear function. Y equals, negative 1x minus 5. The slope of this line is negative 1. No matter where you're at, whether you're at x equals negative 3 or any other point on the line, the tangent line is the line. If you go in the direction that the curve is going in, you're going in the direction of that line. So the slope of the tangent line is the same as the slope of the line, which is negative 1. So I'm going to save myself some time and just enter this, right? Those are the only ones that you can really do this for. All right, just lickety split like that. -1. All right, so one of those is done. And you see that there is no red line here. The tangent line anywhere is that line. The end. Right. So here's not a line. All right, so this one's using the second limit definition. So I'll write this one up. So the function is the square root of x plus 6. And we want the slope of the tangent line at the point where x equals +3. Right, so this time again, I will not make a graph. I've done a bunch of problems already where I made a graph. All right, again, a graph will just kind of tell you if the slope should be positive or 0 or negative, So I'm going to just write that. Now the second definition, slope of the tangent line. This is the one where you have, you're at 3, and then you go to 3 plus h, and then have h approach 0. So limit as h approaches 0 of the value of the function at that 3 plus h minus the value of f at 3. All right, that'll be the rise for the slope of a secant line divided by, and then this h represented the run. 3 plus h minus 3 would just be h. So those are the slopes of the secant lines, and we're going to get the slope of the tangent line by having h go to 0, right? That way 3 plus h will get closer to 3. All right, so I substitute for all this stuff. We got the limit as h approaches 0. Now the value of f at 3 plus h, you just replace x with 3 plus h. So that'd be the square root of 3 plus h plus 6, which will just be h plus 9. I'll write that in a second. Then minus the value of f at 3 is the square root of 9. 3 plus 6 is 9, and that's just 3. And so it's plain old 3. And then all that divided by h. So like I said, this is limit as h approaches 0 of the square root of h plus 9 minus 3 in the numerator and h in the denominator. So at the moment, right, it's one of them 0 divided by 0 limits. So like the one earlier with the square roots, right, I'm going to multiply the top and bottom here by the conjugate of this radical expression, right? So that'd be the square root of x plus h plus 9, then plus 3, and do the same thing down here. And in the numerator, we just get h, right? Already almost an hour and a half in. I'm going to skip some algebra steps if need be. Square root of h plus 9 squared would be h plus 9. Then you'd have minus 3 squared, which would be minus 9. H plus 9 minus 9 would just be h. And then down here, h times that conjugate, square root of h plus 9, plus 3. Then the h's are going away, right, leaving me with 1 in the numerator. And now I have an expression where I can pop 0 in. H approaches 0, numerator is 1. And then the square root of 0 plus 9. Square root of 9 is 3. 3 plus 3 is 6. So the slope of this tangent line they're talking about is positive 1/6. Again, the picture there, great. All right, another quadratic. This time, using, so once again with that second definition with the h, like I've been saying though, if you like the first definition better, you can keep using it. I personally like that first definition better. I feel like there's less writing involved. But I will still go through the other definition here. So our function is this quadratic, negative x squared plus 3x minus 4. And we want the slope of the tangent line at x equals 1. So the slope of the tangent line will be, and this is the one where, you're at 1, and then the other point is at 1 plus h, and then you have h approach 0. So that 1 plus h will get closer and closer to 1. And then the slopes of our secant lines, you'd have the value of f at 1 plus h or h plus 1, same thing, minus the value of f at 1, so there would be the rise of a secant line, and then the run would just be this h. So I got the limit as h approaches 0. Now, the value of f at 1 plus h, just go through the rule, replacing all the x's with 1 plus h. So I have the opposite of 1 plus h squared plus 3 times 1 plus h, and then minus 4. Right, there is f at 1 plus h. And then minus f at 1 would be negative 1, plus 3 is positive 2, minus 4 is negative 2, right? That's the value of f at 1. So minus negative 2, and then all that divided by h. And then we simplify, of course. Now remember, order of operations, you would square something first before doing multiplication. This is the limit as h approaches 0 of the opposite of. Now when you square 1 plus h, that is not 1 squared plus h squared. Remember, you do not distribute powers. That's 1 plus h times 1 plus h again, and then you FOIL. So that's 1 plus 2h plus h squared. But we're going to distribute the negative there in a second, and then, plus all this. You know what, I'll do this distributing of 3 here. So you got plus 3 plus 3h, right? 3 times 1, 3 times h. And then minus 4 plus 2 would be minus 2. Right, minus 4, and then this would be plus 2 for minus 2 there. All divided by h, and I'll just do this. And then we got to distribute this negative, right? We're taking the opposite of this thing squared. So we have the limit as h approaches 0 of. Now, look at all the stuff that would go away. You have negative 1 here, plus 3 minus 2, that'd be 0. So the constants, the things without h, are gone. And then I would have, negative 2h plus 3h. That'd be positive 1h. Again, that's negative 2h plus 3h, positive 1h. And then negative h squared. So all I have left over up top is 1h minus h squared. Combining like terms, I was just doing that out loud without writing it, sorry. Now still, I can't plug in 0, but if I divide each of these by h, now we have this, right? The limit as h approaches 0, or you could factor h out of the numerator and cancel it, the denominator h. But h divided by h would be 1 minus, and then h squared divided by h, just be h. And now I can pop in 0 for h, and this should just be 1 minus 0, or 1. All right, so after all that, the slope of the tangent line to this curve at the point where x equals 1 is 1. So you'll see a line with a slope of, positive 1 showing up in the graph that they have here for you. But I'm just popping 1 in there. Great, and that one's done. And then here's the picture, right? Remember this was a quadratic parabola thing. Here's the point at x equals 1. See how the tangent line to that curve at that point has a slope of 1. And that's what we found. All right, so this is back to finding the equation of a tangent line, right? So I need the point on the curve and the slope of the line, the tangent line, and then we can write the equation for it. And it looks like, once again, I'll be putting it in slope-intercept form, right? They got the y equals here, so I'll put it in that y equals mx plus b form. All right, so it's another one that I've done a similar problem for, so I'm not going to graph it again. So we have f of x equals the square root of x plus 4 at x equals 5. So the point on the curve that our tangent line is going to be going through has x equals 5, and then I need f of 5. Now the y value at 5 would be the square root of 9, which is 3. All right, so we're at the point 5, 3. Now I need the slope of the tangent line. Right, so I got a point. I also want the slope. Now I'm going to use that for, again, I like that first definition personally. So I'm going to have, we'll be at x equals 5, and then at, some other value x that's not 5. And then we'll have that value of x approach 5, right? So the limit as x approaches 5 of the value of f at this other x minus the value of f at 5, divided by x minus 5. There's the slopes of any secant lines, and then we'll have x approach 5, so you get closer and closer to the tangent line. So this is the limit as x approaches 5 of, f at x is just this, that was given. This is square root of x plus 4 minus, we just saw f at 5 is 3. So that's in the numerator. And then the denominator has, only x minus 5, so I'm gonna put that in parentheses. That's the only factor down there for the next step, right? Because right now it's the 0 divided by 0. So I'm taking the entire numerator, the entire denominator here, multiplying, this is one of those with the square roots. So I'm going to multiply by the conjugate. That would be the square root of x plus 4 plus 3. And do the same thing down here. So we have the limit as x approaches 5 of. All right. So again, I'm going to rush through some of these. We're over an hour and a half in. This is x plus 4 minus 9. So the numerator would be, this would be x minus 5, and then that would cancel this x minus 5 down here. So I have 1 left over in the numerator, and then that conjugate, right, square root of x plus 4 plus 3 down here, and that's 1/6. Right, because when I plug in 5, this would be the square root of 9, which is 3. 3 plus 3 is 6. You got 1 in the numerator, 6 in the denominator for this limit. So the slope, 1/6. Now, that's not the answer. I just circled it, but it's my slope. What they want was, the equation, right? The equation of my tangent line. So I'll put that here, actually, more space. So remember, in point slope form, real simple. Change in y. So y minus, the y coordinate of my point, y minus 3, equals the slope, okay, 1/6 times the quantity, and then the change in x, right? X minus the x coordinate of the point we have. Now, I'm going to check something. They have y equals, so I'm just going to add the 3 over here. So we have y equals, and I'll keep it the way it was. You have 1/6 times the quantity, x minus 5, and then plus 3, I added 3 after. I'm going to put this in. Now, it's not in slope-intercept form, right? You'd have to distribute the 1/6. So you have 1/6x minus 5/6, plus 18/6. So that'd be, if you were to go all the way, 1/6x, again, minus 5/6, and then this would be 18/6, so plus 13/6. Now there's slope-intercept form. That's totally fine. I'm going to type it like this just to see, because they don't say anything about slope-intercept form. Right? They just have y equals. So as long as I put in something valid, should be good. So 1/6 times, x minus 5, and then plus 3 after, and see what happens. Wonderful. Okay, so you can do that. So they didn't mention anything about slope-intercept form, so as long as you're putting an expression in there that's equivalent to slope-intercept form, you should be good. So yeah, see the plus 13/6, 1/6 x over 6 plus 13/6 there. They actually went all the way to slope-intercept form. And all that. And there's a picture again. Cool. All right, so same deal, right? Find the equation of the line tangent to some, it's another rational one at x equals 3. So again, I like doing that first definition. It says use a limit definition, right? So I'm going to do that first one. So our function is 3 divided by x minus 2. And we're talking about the equation of the tangent line at the point where x equals 3. All right, so our point is going to be 3 and then f of 3. All right, plug 3 into the function. And when x is 3, 3 minus 2 is 1. 3 divided by 1 is 3. So 3, 3 is the point on the graph. And we want the tangent line, and we want the slope of that tangent line. So again, I'm going to do that first one where we have a value of x that's not 3 approaching 3. The limit as x approaches 3. The value of f at x, 3 over x minus 2, minus, and then the value of f at 3, which is just, 3. And then divided by x minus 3, the change in x. All right, so another 0 over 0, 1. So I'm going to multiply the top and bottom. Now the only denominator I see is this x minus 2, so I'm going to multiply the top and bottom by the quantity x minus 2. This would have to be distributed, right? There's a subtraction up here. So we get the limit as x approaches 3 of, this first fraction up here, the x minus 2 would cancel. I'd be left with just 3. Then minus, and then you got 3 times the quantity x minus 2 in the next term, divided by, and then this product down here, x minus 3 times x minus 2. Now here, when I simplify, I distribute the negative 3. And this stuff up top would be negative 3x, and then plus 6 plus 3, that'd be plus 9, which is negative 3 times x minus 3, and then the x minus 3's would cancel in the numerator and denominator. So I end up with this, the limit as x approaches 3 of negative 3 in the numerator, and then just this x minus 2 in the denominator. And so we're getting negative 3 over 1, right? Negative 3 when I plug in 3 there. So slope is negative 3, and then we can write the equation for our tangent line. Oops, equation. So it'd be y minus 3 equals, the slope, negative 3, times the quantity x minus 3. And if I add 3 to both sides, you get y equals, negative 3 times the quantity x minus 3, plus 3. And like you saw in the last example, I can just enter this if I want. But this one's not so bad to go to, there's no fractions or whatnot. So I'll distribute the negative 3. That'll be negative 3x, and then plus 9 plus 3 for plus 12. So there's the equation of the tangent line in, slope-intercept form. So here, negative 3x plus 12. Cool. All right, so those are done. Now, that's the one section, all right, the tangent line stuff. And again, here's a picture once more. Tangent line, 3, 3, and all that, negative slope. So now we're moving into the other section, right? So that was the tangent line section. So now we're into the derivative of a function at a point. This is no different, right? Either one of these is no different than the tangent line part. All right, it's just another name for it. Now there will also be some new notation involved, I'm sure, which I'll point out. So look, see this f prime with the 4 in it there? There's this f with the apostrophe that's going to be set as f prime quite often. This means find the slope of the tangent line to the graph of f at x equals 4. So it's real, again, it's no different, but I will write this out. All right, I will write this out, this new notation and this new word called the derivative. So the slope of the tangent line to say f of x at x equals a. So again, before we were calling this, m subtangent, means exactly the same thing, right? These are interchangeable. So when they ask you for the slope of the tangent line to a curve at some value, at some point, it's the same thing as asking for the derivative. Right? Same thing, the derivative of a function. So the derivative of f of x at x equals a. But the notation here, okay, that's being introduced in this question. There's also some other notation we'll get to, but if it ever comes up. But for right now, we're only seeing the name of the function, and then this apostrophe added to it. F prime will be said at x equals a. So yeah, the way this is said, I would say it's going to be f prime at a, and x equals a. All right. So you hear me say f prime. See this little apostrophe on the name of f. They're asking for, again, what's called the derivative of the function at a, which is no different than the slope of the tangent line, right? So you could say that f prime at a is the limit as x approaches a of f of x minus f of a divided by x minus a. Remember, this was the one definition, or equal to the limit as h approaches 0 of the value of f at, a plus h minus the value of f at a divided by h. Right. Okay, so no different. It really is no different. So I'm not going to draw graphs again. Right? They might have it up here, but we'll probably have a graph in the answer explanation that I'll show you. But so this problem I'm looking at here, we got f of x equals 3 divided by x minus 2. And we want to find f prime at 4. So again, all this means is what's the slope of the tangent line at x equals 4. So it's the same stuff from earlier in the video. So f prime at 4. And it doesn't say anything about a particular definition. It just says use the definition of a derivative. So we can use either definition. All right. So again, I like the first one. So I'm going to have the limit as x, let's take some value of x that's not 4 and have it approach 4. And then, the change in output is the value of f at x. So this 3 over x minus 2 minus, and then the value of f, at 4 would be 3 over 2. Right, 3 over 4 minus 2. So minus 3 halves. And then divided by, x minus 4. So again, we have one of those complex fractions. Multiply the entire thing up here and this down here by the LCD, or at least common denominator, which will be 2 times x minus 2. And this needs to be distributed up here, right? There's a difference, subtraction. So we have the limit as x approaches 4 of, first one would just be 6, right? X minus 2's would cancel, so 6. And minus, and then here the 2's would cancel, so 3 times the quantity x minus 2. So that's the numerator. And then down here we have these three factors. I'll put the number in first. 2 times x minus 4 times x minus 2. Now up top, if I distribute the negative 3, we'd have negative 3x, and then plus 6 again for plus 12, which would be negative 3 times x minus 4, and then the x minus 4's would cancel. So I have the limit as x approaches 4 of negative 3 left over in the numerator, and then 2 times the quantity x minus 2 in the denominator. And if x was 4, you'd have negative 3 in the numerator, and then 2 times 2, 4 in the denominator. The slope of the line in question, this f prime of 4, is negative 3/4. Right, so see, no different. It really is no different than questions in those first three objectives. That's it. Again, the answer explanation. They don't have a graph. Well, they've had enough of them in the first three objectives. But yeah, if you were to graph this function f, plot the point, 4 comma 3 halves, draw the tangent line. Again, the tangent line should have a slope of negative 3/4, right? It would be falling as you go to the right, going down as you go to the right. All right. So here, identify the derivative as the limit of a difference quotient. So another new way of expressing something we've already seen. So remember that f prime just means, slope of a tangent line, derivative. The difference quotient of a function were those slopes of secant lines. So these words, difference quotient, of a function, say of f of x, has the precise same meaning as the slope of those secant lines. Remember the m sub sec earlier. So this difference quotient of some function can be expressed as either, the value of f at some x minus the value of f at a divided by, x minus a, or the value of f at some a plus h minus the value of f at a all divided by h, right? Remember these two expressions kept coming up. These represented, the slope of a secant line, right? From the point at a to the point at x, or from the point at a to the point at a plus h. And the words difference quotient are just some fancy words for the same thing. Now, what you're asked to identify in this question, look back at the question. You're given this limit of a difference quotient, right? This expression here after the limit represents the slope of a secant line to some given function. So it says the limit given below represents the derivative, right? The slope of the tangent line, which is the limit of the slope of a secant line, the limit of a difference quotient of some function f at some number a. What is the function f and the number a? All right, so I gotta mess with this a little bit because this is involving that h, right? So it's got to be something. It's got, the difference quotient here is in this form. So look, we have the limit as h approaches 0 of, and then here is the difference quotient. You got, I'll write it the way they have with the brackets. You got 9 times the quantity 2 plus h to the fourth plus, and then negative 6 minus 3h, and then plus 10, close the brackets there, minus 148, and then all this divided by h. All right, so you see how this is in this form here, right? So this expression in the brackets, this here, must be the value of f at, a plus h. So we just have to determine what the a is. Now, based on the fact that this first term has 2 plus h in the fourth power there, I guess that a must be 2. All right, that's 2 plus h instead of x. So I need to rewrite this expression here so that another 2 plus h shows up, which will be pretty simple. Just factor out negative 3. And then this, 148, this here, right, that would be the f at a. So we also should have a function where f at a, right, which is, I said a is 2. We need to have a function that when I plug into the output's 148. So look, so the value of f at, looks like 2 plus h is 9 times 2 plus h to the fourth. And then from this term here, this quantity and the negative 6, minus 3h, if I want 2 plus h to show up, I'd have to factor out negative 3. Right, if I factor, so plus negative 3, which would just be minus 3, factor out negative 3 from these two, and then you'd have the quantity 2 plus h again. And then you got, plus 10. So you see how now there's a 2 plus h here, 2 plus h here. Those replace x in f of x, right? So f of x must be 9 times x to the fourth minus 3 times x, right, wherever the 2 plus h is, and then plus 10. This must be the function f of x, and then again, the value that we're taking the derivative at must be 2 based on the way this looks. Now let's double check, make sure that the value of this function at 2 must be positive 148. 2 to the fourth power is 16. 9 times 16 is 144. And then plus 10 is 154. Then minus, 3 times 2 is 6. 154 minus 6 is 148. So this function works for everything that's being expressed to us here. So back here, the function they're taking the derivative of, f of x, will be 9x to the fourth. Oh, not dollar sign. 9x to the fourth minus 3x plus 10. And the value at which they're trying to find the slope of the tangent, right, that they're finding the derivative at, must be 2, right? Because again, it was 2 plus h here in this power of 4. And I could rewrite this as something times 2 plus h. and please read through the answer explanations and all this. Great. So once again, back to this objective. Now I've already told you linear functions should be easy, quick, and simple when it comes to finding the slope of a tangent line or a derivative. This is a linear function, right? If I looked at the graph of this, it would be a straight line graph. So at x equals 10 or at anywhere for x, the slope of the tangent line will just be the slope of this line, right? The tangent line is just this line, which has a slope of -7. So this f prime at 10, and that's the slope of the tangent line to f at x equals 10, should be -7. So I'm not going to write that one out. I've already mentioned that plenty, how linear functions should be quick and easy. Now they go through it, of course. You can read that if you want. So now, okay, this notice, right? They're not asking us to actually find the derivative or the slope of the tangent line to this function at x equals -1. We're asked to, given this function, write the limit representing the derivative and using h. So that was that second definition. So here's what they want you to type in. So notice they already have the limit as h approaches 0 right there. So what you're filling in the box here is that difference quotient, right? Putting the slope of a secant line expression in here. So, of course, I'll show you. Now, you don't have to simplify it. They didn't say anything about simplifying it, so I'm just going to type in as is. So we're given this function. It's quadratic function. You got 5x squared plus 8x minus 7. And we're asked to represent, right, f prime, right, the derivative of f at x equals -1. So remember that second definition, f prime at -1 would be the limit as h approaches 0 of. So here's what we're going to type in. In the numerator, you have the value of the function at, -1 plus h, or h minus 1. Then minus the value of f at -1. That's all the change in y in the secant lines, right? And then divided by h. Now this is the limit as h approaches 0 of. So this here, I'm just going to go through the rule and replace all the x's with -1 plus h. So that's 5 times -1 plus h squared plus 8 times -1 plus h, the quantity, -1 plus h. Right, then minus 7. Right, so maybe put this in parentheses or brackets just so you know that this whole thing here is this, right? F at -1 plus h. Then minus, and then the value of f at -1 would be, 5 plus -8, so -3 minus 7 would be -10. So I'm just going to call that, plus 10. And you could even simplify further, but I'm just going to type this as is, and then all that, divided by h. All right, so there, I'm going to type this in. This is what they want me to do. All right, that's all they're asking you to do. All right, so the limit as h approaches 0 of, so in parentheses in the numerator, another set of parentheses for this f at -1 plus h. So I have 5 times the quantity, lots of parentheses, -1 plus h squared plus 8 times the quantity, -1 plus h. and then minus 7, close that set, and then plus 10, right? That was minus negative 10. So that's all in the numerator divided by h. So there's f at negative 1 plus h minus f at negative 1, all divided by h. That is what they're asking you to put in. All right. So I think they might, oh, they actually went and simplified it, right? But notice they didn't say anything about simplifying it. So yeah, if you were to totally simplify this expression here, it would simplify to 5h minus 2, which would be less to type in. I guess if you want to type less, then go ahead and simplify, but you don't have to. All right, so once again, finding the slope of a tangent line to some function at a particular value, which is represented here by f prime at 10. So f of x is the square root of x minus 6, and we want to find f prime at 10. So again, I'll use that first definition. Got the limit as x approaches 10 of the value of f at x. All right, this is an x value that's not 10, minus the value of f at 10 is 2, right? That'd be the square root of 4. And then divided by x minus 10. So once again, I would do the whole multiply by the conjugate thing, right? It's the square root, so everything up here, everything down here, times conjugate of the radical expression. That's the square root of x minus 6 plus 2. Same thing down here. And we have the limit as x approaches 10. Now up top, that'd be x minus 6 minus 4, so that'd be x minus 10 up top when you totally simplify, and that would cancel with the x minus 10 down here. So I would just have 1 over that conjugate, square root of x minus 6, plus 2. So this is 1/4. There's f prime at 10, right? Plug in 10, you have square root of 4 is 2, 2 plus 2 is 4. So yeah, the slope of the tangent line to that curve, right, wherever that graph of that function looks like, at the point 10, 2, the line that's tangent has a slope of positive 1/4. So again, derivative is not a line, so I actually have to go through it. So find f prime at, x equals -4. So here's our function. Right, some quadratic. Got -2x squared plus 4x plus 13. And then f prime at, -4 we're trying to find. So I'm going to use that first definition again. I prefer it. So this f prime at -4, it's going to be the limit as x approaches -4 of f at x, which is this -2x squared plus 4x plus 13 minus, and then the value of f at -4. Let's see, -4 squared is 16 times -2 would be -32 for the first term. And 4 times -4 is minus 16 for that term, and then plus 13 for the third term. So overall, -32, -48, plus 13, negative 35. All right. So minus, negative 35, the value of f at negative 4. And all that, that's the change in the outputs, the rise, and then the run would be x minus negative 4, right? The change in the x coordinates, or x plus 4. Okay, so another 0 divided by 0, 1. So I gotta manipulate this a bit. All right, simplify it. And the limit as x approaches negative 4 of, this would be negative, now, this up here would be negative 2x squared plus 4x. And then this is 13 plus 35, right? So that'd be plus 48. And I notice that these all have 2 in common, and being that the lead is negative, I'll factor out a negative 2. And if I do that, the other factor is x squared minus 2x, then minus 24, which, this factors to x minus 6 times x plus 4. And then down here we have, just the factor x plus 4, right? So these x plus 4s are going away. And I'm left with just, negative 2 times x minus 6, where if x goes to negative 4, it'd be negative 4 minus 6, negative 10, negative 2 times negative 10, positive 20 for the slope of the tangent line to this curve, this parabola at the point where x equals negative 4. So 20 is the slope of our tangent line, this f prime at negative 4. Cool. All right, so another objective done. All right, so this one again is where you're pointing out what the function is and at what value are we finding the derivative. So you see how this first part of the expression is 3 over, and then instead of x, you got negative 10 plus h. So the value, right, remember f at a plus h, so it looks like a is negative 10, and then the function we're plugging into is 3 over x, right, because this would be 3 at negative 10 plus h minus 3 at negative 10, right? If this is f at negative 10, if this was my function and I plugged in negative 10, the value would be negative 3/10. So when I go minus negative 3/10, that's why I got the plus 3/10 here, and then all over h, and the limit as h approaches 0, right? This would give me f prime at negative 10, or the slope of the tangent line to 3 over x, y equals 3 over x at negative 10. Hopefully you can just kind of look at these, most of them, and be able to tell what those are, or what function they're taking the derivative of, and where are they taking the derivative. Same thing here, right? This would be the 4th root of x, but notice how they plug in 13 plus h plus 13. So the value we're starting at is 13. That's the a. So the value at 13 needs to be the 4th root of 13, and the value at 13 plus h is this 4th root of 13 plus h. So the function that's being plugged into up top here is just the 4th root of x. So let me see, I got there's a root thing where I can put in a different index, so 4th root of x, right? That would be the function we're plugging into, right? 1, you plug it in, h plus 13, 13 plus h, minus, and then the value at 13. So this expression here, this limit, is representing the derivative of this function, this 4th root of x, at x equals 13, right? Or you could call it f prime at 13. Okay, so that one's done. That one, hopefully, I know there was one earlier with a quadratic or a polynomial involved. It was a little trickier, but hopefully these are relatively simple to identify what function are you taking the derivative of and where are you taking the derivative at. All right, so we're done with that. section. That was the derivative of a function at a point. So finally, we have velocities and rates of change. So the only objective left is, use the concept of a derivative to find an instantaneous velocity. So let's go over that concept real quick. So velocities. So if you're given a position function or displacement function, right? Something that indicates your location, how far you are from something, right? A position. S of t. So it doesn't have to be f of x all the time. So again, this represents your position in some sort of distance units, right? Just a distance traveled, how far away you are from something. So this could be like meters or feet or miles, right? Whatever, right? Something, the S of t, where t represents how long you've traveled for time, and this could be in in seconds, minutes, hours, days, whatever, years. So you have a position function given. I'll show you a little graph here. So again, the horizontal axis, the input axis will be time, and the vertical axis will represent, position, which is, represented by this S in a lot of these examples. So in this particular Newton stuff, S, might represent distance. So here's the graph, right? So now usually we start at time 0. There could be like negative time if you look back in time or whatever, right? So like here's some function, S of t. Now, velocity. There's a difference between average velocity and this instantaneous velocity that they're asking about. So average velocity, so I'm going to call it V for velocity with AVE as a subscript for average. This is over some interval. So from say t equals A to t equals B. So if you want to talk about the average velocity at which some object was moving, the average velocity, it's almost like a speed again, but speed can't be negative, but velocities can be negative. What you're talking about is this. So say here's t equals A, and I let some time pass to t equals B. Well, I'll be at a different position, depending on what the curve looks like, function is. So here's the position, S at A. And at time B, here I'm at this position, S of B. So the average velocity is simply the slope of a secant line. It is how much did your position change over that period of time. So it's a rise over run. So the slope of a secant line, and that secant line would look like this, and I'll make it like a dotted line here. Through these 2 points, there's A, S of A, B, S of B. Here's a secant line, right? So cutting through 2 points like this on the curve. So your average velocity, from one time to another is again, how much did the position change? So that would be, the position at B minus the position at A. It's how much did the position change divided by the change in time, which is b minus a. So it's like rise over run, right? Change in y over change in x. Now you might also see this represented as, delta S over delta T, right? Remember, delta means change in, so change in position over change in time. So that's average velocity over some change in time on the, time axis. Instantaneous velocity is different. Instantaneous means at one instant. So this isn't from one time to another. This is at time, say t equals a. Now this is going to be represented by just velocity at, time t. So say velocity at, I'll say at time a, right? So v of a. So here's time a. So again, I'm at this point a, comma, the position at a, s of a. This instantaneous velocity at a particular point, one moment. This is your slope of the tangent line there, or the derivative. This is your slope of tangent line. So in my picture up here, that would be this line. And again, it's tangent to the curve. So there's your tangent, at x equals a t equals a at time a. And the slope of that tangent line tells you how fast the position is changing at that moment, right? The speed at which the position is changing, your velocity at that moment. So remember, the slope of tangent line is the derivative. So if the curve I'm looking at is this S curve, right, the position function, then the velocity at A is S prime at A. Okay, so this is what we're going to be using here. And S prime, right, the derivative is exactly like F prime I was doing earlier. So we can have T approach A, and I'll write all this up on, no, I'll just do it here. There's some space over here. So S prime at A, right, or the velocity V at A. And I got the two definitions. We could say it's, I go at A and then I pick some T value that's not A and have it approach A, right? I do the limit as T approaches A, as time approaches A seconds of the position at T minus the position at A, right? There's your rise, change in position over the change in time, T minus A. Now for velocities though, right, the numerator is in meters or feet or miles, right? This is your distance. The denominator is in, seconds or minutes or hours. So this will be in like feet per second or, meters per second or miles per hour or some kind of thing like that for velocity, where you have a distance unit in the numerator and a time unit in the denominator because it is a change in distance over time. Okay. Or, and the other definition was I go from A to A plus H and then have this go to A by having H go to 0. Right? Do the limit as H goes to 0 of the position at A plus H minus the position S at A divided by H. Again, H here is the change in time now, the horizontal change. So same definitions for, again, S prime at A, or this, instantaneous velocity, the velocity of an object at a seconds. So really not a whole lot different than your tangent line to a function earlier in the video. It just has some units involved now, right? There will be units involved. Meters, miles, feet, for position, seconds, minutes, hours, whatever for time. Okay, so here. So all the stuff I did earlier with, functions of x, you're doing exactly the same thing with functions of t. So here, the position in feet. So s of t, s represents position in feet of an object moving in a straight line after t seconds. So t represents time in seconds. Is given by this function here, a nice quadratic function. You're asked to find its instantaneous velocity at, t equals 1. So this is 1 second. So this is no different than if I had f of x equals negative 2x squared minus 5x plus 2, and I said find the slope of the tangent line at x equals 1. This is no different. It's just going to have some units involved, feet and seconds or feet per second when I calculate velocity. So once again, s of t is negative 2t squared minus 5t plus 2. And we're asked to find the velocity at time equals 1 second, right? So velocity of 1, or we could call this s prime at 1. Okay. So like I said before, I like using the first definition a lot more than the second one, so I'll keep doing that. So I'm going to take the limit. So I take a time called t that's not 1 and have it approach 1. So the limit is t approaches 1 of, and then, the position at time t minus the position at the 1 second. There's your change in position. So that'll be in feet up here. Some sort of, because the positions were given in feet per, and then the change in time t minus time, 1 second. This will be in seconds. So the output, the velocity here is going to be in, feet per second units. I don't see the units in the problem, so I don't know if you have to type in the units. So I'm going to type in the number when I get it and see if it's considered correct. They should technically have the units feet per second here though. Anyway, so let's go through this. It's just like with x earlier. It's no different than having x, but instead here you have t. Right? You got the limit as t approaches 1, and then s, the position at time t, is given here. Negative 2t squared minus 5t, plus 2. I'll put that in parentheses, right? That's the position at time t, even though you don't need to. It's not being raised to powers or multiplied by anything. Then minus, and the position at 1, plug in 1 for t. This would be negative 2 minus 5, which would be negative 7. Plus 2 is negative 5. All right, so negative 5 feet. So that just means I'm 5 feet below or 5 feet, in the negative direction away from my starting position, or away from the 0 mark, whatever the 0 feet mark is. I'm 5 feet, below that or left of that at time equals 1. Then divided by, and then t minus 1. Now this is another one where if I were to just plug 1 in, 0 divided by 0. So I manipulate this. Okay, so we have the limit as t approaches 1. Up top, this is negative 2t squared minus 5t, and then 2 plus 5 is plus 7. Now, I like having positive lead coefficient of my polynomials, so I'm going to pull out a negative from that. So factor out the negative 1, and then we have 2t squared, plus 5t minus 7. And that's nice and factorable, right? And the only factor in the denominator is t minus 1. And then this 2t squared plus 5t minus 7, this factors. I would factor negative 14. Yeah, it would be 7 and negative 2, right? So plus 7 here, minus 1 here. So I would factor 2t plus 7 times t minus 1. And these t minus 1s would then go away. So I have the opposite of the quantity 2t plus 7. And if t were 1, this is 9. So negative 9 for the velocity. Negative 9, feet per second. So you'll see later, there's going to be another video later where we talk about motion more than just this slope of a tangent line deal. Having a negative velocity just means that you are moving in the negative direction. There will be a positive direction and a negative direction. Having a negative velocity simply means you're moving in the negative direction, right? Or if you were to graph this position function, look at the point, 1, negative 5 on that graph. The slope of the tangent line would be negative 9. Right? So yeah, so again, I don't see the units here. And it didn't say anything about typing the units in. Usually they have like the units after here, feet per second. So I'm just going to type the number, right, negative 9. And hopefully that's good enough and they don't want the actual units. All right, great. But if you look at the, no, they don't even write the units here. Technically, the units should be there, right? It should be in feet per second, this velocity. So please keep that in mind. Okay. So more of the same. All right, this is the only objective left. All right, so this is making a table of, remember I mentioned average velocities. Right, these V abs, these are slopes of secant lines. And then you're asked to approximate the instantaneous velocity based on these average velocities as the value of t gets closer and closer to 2. So you're using slopes of secant lines, average velocities as the time gets closer to 2 seconds to then state what the velocity at 2 seconds should be. Now, this is a function that you could find the velocity yourself and using one of the definitions, but they're asking us to fill in this whole table here, so we will do that. So what I'm going to do is I'm just going to make an expression for the average velocity from time 2 to time t. So here's what I mean by that. So here's again, here's your position function. So again, s of t, position at time t, is represented by negative 4 times t cubed minus 1. And this is in they don't even say if it's feet. The position of an object moving along a straight line. Yeah, so it's just the position on some number line. So it could be in feet or just units, distance units. They don't really give us any. And again, they don't really have you typing in units here, so it doesn't really matter all that much right now. So we're asked to, estimate the instantaneous. Now I know they put the I and ST down here. What's the velocity at time equals 2? Or, S prime at 2. Right, again, the velocity is the derivative or slope of the tangent line to this position function. So remember the definitions. Now I'm just going to use this one. So we got the limit as t approaches 2, right? So I'm going to do that one where we're at 2 and then some other value of time that's not 2, right? And then have that approach to of s of t, the position at time t, minus the position at 2 seconds, then divided by and t minus 2, the change in time. Right, so here are the average velocities they're talking about, right? V avs. And when we have t approach 2, then we'll have the instantaneous velocity. But I'm going to let's look at those average velocities, right? Because I need to make a table, fill in a table for them. So these average velocities. So the average velocity, now this is again from time 2 seconds to t seconds is what I have here. And that's s of t minus s at 2 divided by t minus 2. All right, so filling some stuff in here. S at t, the position at time t is given here. So that's your negative 4t cubed minus 1. Then minus, the position at time 2. Now 2 cubed is 8. Negative 4 times 8 is negative 32. Minus 1 is negative 33. And then this, divided by t minus 2. All right, so we could simplify this a bit. Now you can actually just type this in. I'm going to go to Desmos in a second. But I'll simplify it first. We got negative 4t cubed, and then minus 1 plus 33. So it'd be plus 32 in the numerator, and then t minus 2 in the denominator. And honestly, I mean, unless you remember how to factor really well, which I'm hoping you do, you could go further. Pull a negative 4 out top, and then you have times t cubed minus 8 divided by t minus 2. And then this is a difference of cubes, t cubed minus 2 cubed. So that would factor to t minus 2 times t squared plus 2t plus 4. And then the t minus 2's would cancel. And then this expression, if I distribute the negative 4 back, you got negative 4t squared minus 8t, and then minus 16. This expression right here represents the average velocity from time equals 2 seconds to another time called t seconds. So I'll put both of these in and show you that they're the same. All right, so I'm going to go to that Desmos site. All right, desmos.com, free online graphing calculator. I'm not going to worry about graphs so much here, just these expressions. So one of these, right, I said, I don't want to put t in. So the thing is, if I put t in, it's going to have me put in like a slider for t. If I want to make a table in Desmos, I got to use x. So instead of x, or sorry, instead of t, I'm going to use x. Right? So here's s of x equals, negative 4x cubed minus 1, right? That was our function. So look, instead of typing in all the stuff I did or writing all the stuff I did, I can just put in an expression. Here's an expression that will represent the slope of any secant line, right? The average velocity at, 2 seconds. So it was s at x. Again, I'm replacing t with x minus s at 2 divided by x minus 2. Now, and don't pay attention to the graph so much, just focus on the values of these average velocities. So let's make a table here, and I'm going to put in, what they had here, right? They're saying we're going from 2 to 2.1 seconds. What's the average velocity? And then 2 to 2.01 seconds. So it's, again, all I have to do is plug in these values, 2.1, 2.01, the values of t from the table here. Because what I have, right, this expression is, this is the average velocity from time 2 to, whatever other time I want, which again, I'm calling it x here. So 2.1, they say go to 6 decimal places, yikes. Well, that only stops at 2, and then 2.01, and then from 2 seconds to 2.001, and I think they go all the way down to, 2.0001, 2 and 1/10,000th of a second. So 2.0001. All right. I hope these are good to. The thing about these tables is sometimes they round before, the 6 decimal places that they want, right? They say round each answer in the table to 6 decimal places, but enter an integer value for the instantaneous velocity at 2, right? The derivative at 2, the slope of the tangent line. So look, if you look at these, it looks like those slopes are approaching, the average velocity is approaching -48. So that is what I'm going to write here in the instantaneous velocity area. And then all these, I'll type in what I've got in the table here, and hopefully things work out. Again, some of these might have been cut off earlier than I wanted, but so we got, -50.44, the average velocity, -50.44, feet per second, from 2 seconds to 2.1 seconds. And let's do a copy paste. Copy that. So there's your velocity from average velocity from 2 seconds to 2.01 seconds. And here's what they have for, average velocity from 2 seconds to 2.001 seconds. And that's 6 decimal places. So I hope it's rounded well. I might have to go deeper here if these aren't rounded well. And then from 2 seconds to 2.001 seconds, and it looks as though the average velocities are approaching a velocity of -48 at 2 seconds. All right, so let's see if that worked out. Good. All right, so those values in the table from Desmos there worked out here. They rounded correctly. Great. And they go through all this. See, do they even have you? Yeah, they're just saying substitute the values in this expression above. So again, I could just have a calculator like Desmos do that for me. All right, so this one's pretty similar. All right, so I'm not going to write this one out. Just go to Desmos, and again, instead of P, I'm going to use X. So just remember that X will represent time in Desmos. So that way I can look at the table. And I'm going to punch in the average velocities from 1 second to, some other, so, to t seconds, which again, t will be represented by x. So all that's going to change here is, the function, instead of it's going to be negative x cubed minus 5, or again, x is representing t. So just negative x cubed minus 5. And then instead of having, to calculate my average velocities from 1 second to other times, I have f sub x minus s at 1. divided by x minus 1, right? That would be your change in position over change in time. All right, so then I need to change this table up, right? I don't want 1, 2, I want to be near 1, right? So we're plugging in 1.1, 1.01, 1.001, and 1.0001, right? And you see at 1, it would be undefined, this expression. Oh, that's because oh, crap, all right. Need to make a new table. Sorry, new table for this, right? That was for the one, that was when 2 was there. See, now it's got 1. All right, so now I want to put in, from 1 to 1.1, then from 1 to 1.01, from 1 to 1.001, 1.0001, and you see how at 1, it's undefined, because we're just seeing, what happens as we approach 1 for these average velocities. Now, looking at the table, it looks like the velocity at 1 will be, -3, feet per second or meters per second, whatever it is. So that's what I'm going to put in for this instantaneous velocity down here, right? They say type an integer there. Looks like the velocity at 1 second will be -3. And then I'm just going to copy paste, again, all the values I got for the average velocities over here, right? So -3.31, feet per second, meters per second from, 1 to 1.1 seconds. That's the average velocity over that interval. And then this for the 1.01. And then this from the 1 to 1.001. And that's not more than 6 decimal places. And then this from the 1 to 1.0001, right? All the average velocities, and once again, it looks as though the average velocities are approaching -3, at 1 second, right? So it looks like you could do that with Desmos, just kind of enter the expression for the average velocity from whatever time they want to some other time, and then you're plugging in those other times. And it looks like you can just copy and paste all those values in here and be fine. All right, so now it's just like a couple problems ago. So I'm not filling in tables or whatnot. I'm actually asked to find, the instantaneous velocity, the velocity of this object, this rock, after 1 second. All right, a rock is dropped from a height of 64 feet. Its height, so it's feet, right? Its height above the ground, t seconds later, is given by this function here. All right, so you see at 0 seconds, you're 64 feet up. That's what they said. And then 1 second later, we'll be at a different position. What we want to know, though, is the velocity at that position. All right, so same definition as your derivative slope of a tangent line for everything in this video. So my position function given by -16 t squared plus 64. And we want to find, again, the velocity at 1 second. Another way of stating this, once again, is the derivative of the position function at 1 second, s prime at 1 second, which using, again, either definition, but like I've been saying, you've been hearing me saying, I like that first definition more. I prefer it. So I'm going to go from 1 second to t, some value t that's not 1, and then have t approach 1. So I'm taking the limit as t approaches 1. And then of all the, the average velocities, the slopes of the secant lines. So the value of the position at t minus the position at 1. And then, the change in time, t minus 1. And this should be in, feet per second again. So you got feet in your positions in feet, your time is in seconds. Which, once again, they don't have this typed in for me, and I don't think they expect it. They just want a number. But know that this should have, feet per second units. So we have the limit as t approaches 1. Now the position at t given here. So it's negative 16 t squared plus 64 minus, and then the position after 1 second, plug in 1 for t, that'd be negative 16 plus 64, or 64 minus 16, be 48. All right, so the rock would be 48 feet above the ground after 1 second. And then divide that by the change in time. So we got 1 second to t seconds, so t minus 1 is the change in time. And we simplify. Right? If I were to plug 1 in right now, it would be that 0 divided by 0 case. So the numerator, you got negative 16 t squared, and then plus 64 minus 48. That's plus 16. All right, divided by t minus 1. Still 0 divided by 0. But this numerator would factor to negative 16 times, t minus 1 times t plus 1. All right, because if I pull negative 16 out, you'd be left with t squared minus 1. Difference of squares, it factors the t minus 1 and t plus 1. So this t minus 1 in the denominator, this t minus 1 in the numerator cancel. And I'm left with this negative 16 and this t plus 1. And if I plug 1 into that, t plus 1 becomes 2 times negative 16 would be negative 32. And again, this would be feet per second. So this, again, being that it is a negative velocity, just means that it's falling down. Right? If you think about, going up is if you think of up as the positive direction and down is the negative direction, which you usually do with like the y-axis on the xy plane, and having a negative velocity would mean, the rock is falling in the negative direction, right, going down toward the ground at a speed of 32 feet per second at that moment. Now, of course, the more it falls, the faster it will get, right, due to gravity. But at that 1 second mark, at that instant, it's falling at 32 feet per second. So I'm just putting in the velocity negative 32 here. Again, they don't have the units for me. You don't have to type the units, just put the number. Wonderful. All right, and great. So that's it for that. All right, decent length video there. So again, hopefully you're looking through and everything I've done here helps you in some way when you work on the assignment yourself. And thank you very much for watching.